We're now going to show how to use a computational chemistry program to determine the dipole moment of a compound. And this is going to use a interface called WebMO and a calculation engine called Gaussian. And so the first thing we do, we need to sketch out our molecule. So the molecule we're going to do is acetonitrile. And so first of all, we choose carbon, and we put a, click here, put a carbon atom, we'll put a second carbon atom, and then we need to put a nitrogen atom. So I'm going to choose nitrogen. I'll drag a nitrogen out, and I'm going to drag back and forth 2 more times to make that a triple bond. And so this should be a CH3 over here, and WebMO has a cleanup system where it will put the right number of hydrogens on. And so we can rotate this around and see it's this right molecule. It's got a CH3 and a carbon nitrogen triple bond, with the nitrogen being the terminal outside atom. So that's the shape of the molecule, and that's reasonably accurate. But now we want to do a calculation to calculate things like the charges on the atoms and the dipole moment. So we'll go to the calculation engine menu. We'll choose Gaussian as our calculation engine. And what we want to calculate is we want to do a geometry optimization. And I'm going to change this to acetonitrile. And we're going to let it do the calculation for us. And that didn't take very long at all. So once we have the molecule, we can see things about it. So first of all, we can look at the dipole moment. And the dipole moment is listed here, 4.04 dBs. If we click on this watch glass, this magnifying glass, we can see that the arrow points towards the negative side of the molecule. So this side down here is mostly positive, and the negative charge is pointing up this way. And that makes sense, not that the negative charge is just on that atom, but that overall the charge, negative charge, goes in that to the upper right direction. It makes sense because the nitrogen is the most electronegative atom, and the hydrogens over here are the most electronegative atoms, so they would be most likely to be positive. We can see the actual charges on each of the atoms, and if we do that, we can scroll down to here and click on partial charges. And the sizes of the atoms here are not the sizes of the atoms. The sizes that are shown are indicative of the magnitude of the charges, both positive and negative, on the atoms. Red stands for negatively charged atoms. Blue stands for positively charged atoms. And so the nitrogen here is negative because it's more electronegative than the carbon next to it. The carbon here is negative because it is more electronegative than the 3 hydrogens next to it. So this carbon is accepting electron density from these less electronegative hydrogens, so the hydrogen is positive, that carbon is negative. This nitrogen is negative because it's accepting electron density from that carbon there, because it's more electronegative than it. So you can tell a lot about the electron distribution in the molecule from doing these calculations.